Hi everyone, I know it's been a while, but I want to do a quick tutorial or partly discussion on CFD or vortex generators, assuming my audience kind of understands fluid dynamics, and you guys probably have heard about vortex generators. It's a pretty popular way of optimizing a fluid system, whether it's a golf ball or airfoil or car or airplane. They're a great way that you can energize a boundary layer and delay stall and try to optimize an object or an aerodynamic object, which really could be anything that travels in the air. And so just to review, hopefully you guys understand that vortex generators are there's a wide range. There is passive and active vortex generators. Active ones are ones that inject or something is actively injecting energy into a boundary layer like a synthetic jet or something like that. But a lot of the popular ways that are maybe for hobbyists or formula students or passive vortex generators. And a golf ball is the most traditional and I think one of the most simplest way to explain it, where you could have a simple golf ball with nothing, it's a simple perfect golf ball with no indentations, and it will fly in the air and it'll create these vortex behind it because there's separation. But if you indent it and have these little divots or dimples, you create mini vortexes on the surface, and those vortex travels down and help energize and actually streamline the golf ball. So in the case of a golf ball, I believe it helps reduce drag and it helps the vortex, the weight kind of stays centralized and together, so the golf balls basically fly farther. And so this is why golf balls have constantly getting better and better, is the optimization of vortex generators. For the most part, there's other things, but when it comes to airfoils, uh, usually what you will look for in a vortex generator is something that will help delay stall or um, increase the lift to drag ratio. So generally before a vortex generator, you have a smooth airfoil, things like this, and then it will stall eventually. And so with the vortex generator, you're hoping to inject energy into the boundary layer to help it remain attached. And so um, they might look like this. You've seen them very popular on cars. You actually um, just like that right here. You guys have
This
probably
is a
seen this on cars, and you might be wondering what they are. And so they're basically vortex generators where the air will hit it and it will create vortex behind it, and it will help minimize drag in the case of a car. And so this is something that, kind of as a spoiler, you can do in CFD, but it's a bit more complex, and it's something that I likely cannot do to I can't demonstrate it in a 1 hour demonstration. It's something that will have to take three-dimensional analysis, because the reality is that vortexes are 3D. I mean, the world we live in is in 3D, so you will have to do three-dimension. And so I'm actually going to show you guys a two-dimensional simulation of this, and you can try look and see the results, see kind of the logic that goes into it. And so I'm going to go into my workbench, and actually I this is going to build off on um, my two-dimensional work. So give me a second, I have to pause something. Okay, and so sorry about that. I'm gonna actually open my workbench. This is the same workbench I've done for almost all my videos. I'm gonna take the NACA 12 and I'm gonna modify it. This NACA 12 is the exact same thing that I did in that other NACA 12 video. So if you have any questions about how I generate this geometry or mesh, look at that video. I'm simply gonna modify it. And so what I'm seeing is basically there's an extrusion here that will induce a vortex behind it. And so how I'm gonna do that in 2 dimension is I'm gonna take an airfoil and I'm literally gonna put an extrusion on it like this. And so in reality, you see this is a 3 dimensional occurrence. So you see actually something like this where it will hit it and it will generate a vortex. And so I hinted it before, but you actually can't do this in 2D. So if you want to do this in 2D because you're just learning this, I'm sorry to tell you, but I'm going to show you right now and I'm going to prove that basically you're not going to get the results you're looking for in 2D because vortexes are in reality are three-dimensional. There's a curl associated with it, and you cannot capture that curl in 2D. But for if you don't believe me, I'm going to show you it right now. So this is my copy. I've already copied it because, and I'll actually compare. There's two types of dimples, or you could either do a vortex generator that's a dimple, kind of a incision, or you can do one that is like this, that blocks it. And this might be more efficient because it creates a vortex, while a dimple will kind of create a vortex, but it also runs the risk of having a trap vortex. Um, and so a dimple is small enough in this case that it won't, but I will show you. So let's open up geometry. And just as a heads up, I might not be able to do many more videos in a few coming months simply because I'm back in grad school, so I apologize. So here's the good old NACA 12 airfoil that I've done in other videos. So what I am going to do, and I've actually never done this before, I'm doing this kind of on the fly. What I think I'm going to do is I'm going to add a little bit of to this airfoil. Like, maybe something right here. A teeny tiny thing that similarly to a vortex generator, the whole point is air is going to hit it and it's going to create these vortex behind it. So as a reminder, right now we basically the fluid around it is an object and we subtracted through a Boolean operation in airfoil, a NACA 12 airfoil that is 1 meter. So you can kind of just use this ruler and you can tell it's 1 meter. Um, and so what we're going to do is we're going to add or we're going to subtract a little bit more to kind of simulate a vortex generator. So how I'm going to do that is I'm literally going to, I actually want to know where this line is. So I might actually have to change that. So this line, this line might not be defined and it's not. So I will define it. And I'm going to move this up to quarter chord just because I can. Actually, it might cause an issue because it's the way that is made, but I can merge that later. So in reality, I drew this initial sketch. I chose that line arbitrarily, which is not great. Now I'm gonna have. Oh no, I should be fine still. Hopefully I am. Yeah, I should still be fine. Um, so I know where that is, and I'm gonna choose this line, this point, as a start. I'm just gonna create a new sketch. And I'm gonna create a rectangle. From here, how big should I want it? Let's make it skinny, big. Let's make it skinny. Let's dimension this. Whoops. So it's starting here, and it is 0.005 meters thick. And so I'm going to actually create a surface from this sketch. But now I have to combine it. I have to create a Boolean, and this will be a unite operation. Oh, sorry. Nope, I was wrong. Subtract it, right? Oh. uh, why is this not working? There we go. So right now the fluid system now goes, it will hit this and it will go around it because this will act like a wall, part of the airfoil. Um, and so when it comes to meshing it now though, remember I have it meshing this way and then I have it meshing down this way. And so I can somewhat just make this come to here, but in my opinion that makes it a little bit hairy. Uh, and I want this to still mesh across here. Um, yeah, this is a little bit hairy, but I'll show you the logic. So what I then want to do is actually I want to create another line that'll go up. So I want to create a new sketch, or sorry, new sketch. I will modify this and I will extend this. Yep. So this should work. We will have to play with the numbers because once we do a face, once we mesh it, these lines want to be meshed all the way here across, and they have to be matching in numbers. And so we added more surface area, so there will be a slight. It's not going to be as like simple as how it used to be. So once I created the sketch, line some sketches, generate this, and so I'm going to create another projection with this edge onto here now. And now I have all of the regions I need, and I have this region. And this region has to be separated because I'm going to be meshing it up and down. So once I'm good with this, you can suppress the line bodies, but I'll do that in the next operation. It's going to ask you to reread it. Yeah, this tutorial is not meant to be a baseline of, academic journals. There are academic journals on similar CFD of vortex generators. Some of them will explore inverse vortex generators like dimples, or extruded vortex generators like similar to what I'm doing. And so there's a lot of modifications we kind of need or that we will need to make. So because there's this added uh, layer, we have this and then now we have this. And so these two things need to add up to here, right? So what we're going to do is we're going to see, all right, my edge sizing, I have 150 and they go on. So if we do 150 on here, here, we know that this has to summate to 150 then on this. But then this will not be equal. Yeah, it can actually summate to 150, but then these two have to be equal. So it's kind of like, uh, yeah, actually it would work. You just have to kind of ignore those two. So 1, 2, 3, 4, 5, 6. I am not gonna do it this much. This seems like, how about I just do 50,000? Yep. So I have 150 here. And now these two parts need to summate to 150. So let me just see this edge. This should be these three. Didn't change at all. Now these four will want to stay this one. Okay, so now it's a little bit tricky because this part together has to combine to 140. I can leave this one, or 300. I can leave this separate. So remember now, from the top side, this is going to come down. It's going to mesh downwards. And these two parts have to equal to 300. So, and I can leave this the same. So there's two more added parts. So we need to add the sizing for this that has to equal to 150. I'm going to change this to simply, sorry. Let's just make this 130. And then we will bias this down. Let's just do the same amount. Oh, did I do 50,000? What did I do? 50,000. 50,000. Now I will insert sizing for these two. This look much smaller, so I will make this 100. I will make this smaller factor, bump this 50. Yeah, that might be fine. We will see if we need to do iterations. So now I have 150 divisions coming this way, and that 150 will match the 150 that I've made manually, 50 here and 100 here. So the last part is simply doing this up-down face meshing. Oh, don't forget to update faces. So I changed, oh, yep, I changed it to be 300. So there's 300 elements from the very top too. So these two parts, this edge and this top edge, has to summate to 300. So I can choose this. Let's do 250. I'm gonna make it hard. Remember, hard forces it to do what you're telling it to. And if you tell it to do a hard operation and it cannot do it, like numerically there's no way, then you will run into issues. It might not ever mesh. It might be in a loading forever. So 250. Alright, these are much smaller elements from this. A little bit worrying. So what I'm going to do is I'm going to actually bias it a little bit. Let's do 100. Just a small amount. Yep. Let's make sure everything's face meshed. Yep. Let's try it. I'm going to pray that this meshes well. And you will know if it doesn't mesh. So this is actually kind of a bad sign. Generally, you don't want to see this type of green. That means something probably is failing. So you can see that some of it have been defeatured. Um, but it's good to see that this part actually was put together. So that's telling me that, alright, let's thinking about it. So you have to make sure that this top side can go up. So this is 250 and 50 summates to 300. That can go straight up. Oh, and that's probably the problem, because we did not. We just made this 300. So we actually need to take this part away. So this 50 edge has to line up to the same 50 edge. And the 200 has to still come with the 200. And I will make this. So now we have 250 there and 50 there. That will summate to the same amount down here. And that should do it. I hope. Be embarrassing if it didn't work. Boom. Looking like it's going much quicker, and there we go. Another issue I see here is this is a change in volume that's pretty steep, and sometimes you may not want that steep of a volume change. But this definition looks good because this is where a lot of the things, the vortexes are going to be created. So let's look at how much computational resources I'm using right now. 150, not bad, so that's why I'm going to double this to about 200, get more definition up here. I could try to get more definition on this backside because this is a little bit worrying. This should be sufficient definition. So I could, on this top side too, I could simply make this more. I could make this 350. And I can lower the bias. And so that's another perk of phase meshing. Phase meshing is substantially much quicker. Hopefully this only takes 10 seconds or so. There we go, a little bit better. Still not the best, but we might be able to get by with it. You can see this area looks pretty decent. Can always be better, but not too bad, to be honest. I could definitely make this more refined. And this is soft. I would actually make this hard. Because then that makes that bias hard. Because right now you see a bit of as if it's a bias on this thing, on this part. And I don't want that. Here we go. Much cleaner. Let's look around. Here we go. This is what I want. This is very clean. Except this is a huge change in aspect ratio. Only way you really could change this or help this is either you simply create more divisions. I can create this part, I can add more and more. I can just continue bumping this up. Just make it 500. Let's make it 10. Since I'm adding more cells, I can kind of do a less of a bias because I kind of care about this change in ratio. So I wanted small cells there, but I also still want this region to be pretty well defined. So that's the thing with CFD is you're always having some type of trade-off of cell size and computational resources, which is related to cell size. So this looks decent. One criticism is I can make this initial size smaller still, and that's defined by here. So I could make this even bigger. I can give this even more divisions. Yep, that's hard. So I could have done this on my own prior, but I didn't want to have to play around too much. But here we've added this area and we've meshed it. So if you're doing something similar, keep in mind that logic that everything, especially in a structured mesh, which is ideal, has to kind of match up those numbers of divisions. And look, this looks much better. This is not still shift in volume, but not as bad as it was prior. And as for Y plus, this is good. So this is 2.5 E here. I will make this 10. Actually, I did this previously, so I'll make this 10. Reference length is still 1. Y plus, that is 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. So that is 3.4 e to negative 5. So we actually are under 1 y plus in this region. The front may be different, but if I simply set it to 10 meters per second, we should be okay in terms of y plus. So let's see how this looks. So here, y plus might not be satisfied, but that's something that you guys know how to adjust it now, hopefully, because I've showed you through all the videos what to do with the mesh. You don't really need to save the when you go in the mesher and you click that save, you really are just saving the full workbench. In my case, I have like a bunch of stuff in this workbench, so it might be taking a while to save everything. But let me get this mesh updated. I'm not going to change the setup too much. I'm going to have similar models. I've done the Spalart-Allmarus model. I will say if you can make the K omega model work, that is kind of the industry standard or most popular if you are using a model like this. Though precision, it's not a big deal. It really just changes the maximum precision. It doesn't change any like local precision, or it doesn't really make it more accurate. It just allows you to possibly make it more accurate, but you guys can look up exactly what that does. So here we have it in Fluent. I'm currently using 2020 R2, which is the most recent as of October 2020. They're always changing, the graphics and the UI changes a little bit, but everything should be the same. Yeah, they added these marks. I don't know why they did that. Actually, one thing I didn't change is I don't know if I changed the boundary conditions. Whoops. Let's see. How do I see? Here we go. Boundary conditions. Display mesh. I want to see the airfoil. And see, right now it doesn't include that, so I actually need to cancel out. This sucks because this would take some time. I don't think you actually have to cancel that out. You simply have to pull up your mesh again and redefine that I want that little extrusion to be part of the airfoil. Right, here we go. So we have the whole airfoil. And remember the inlet, I'm just going to make the whole thing an inlet, even though, oh, actually, good thing I came back because I have to make that. If you forget one of these, you're going to have some type of discontinuity, and that will probably be defaultly set as some type of boundary, but I really don't know what it will be, and that might cause like huge convergence issues, and it would just be wrong. And you could have set those far fields or those upper and lower boundaries as walls as a wind tunnel, but for this purpose, because I'm doing it as probably at a lower angle of attack, it really doesn't make a difference. And so I'm just gonna be setting it to be the same as the inlet. Okay, give it a second. Here we go. We have to reload up the cells, two-dimensional. And so remember I was saying that vortexes in general are three-dimensional effects. And so what I would expect out of this is I would see I feel I would expect to not to be able to capture the effects of vortex generators. Instead, I would imagine simple separation. And so there's many aspects in this analysis of why this doesn't work. One is the turbulence modeling. So I guess the two big parts is the assumptions in turbulence modeling, and the other part is simply doing this in 2D. Vortex generators, I've said this, are three-dimensional effects, and in Spalart-Allmarus, when you, or really in any of these models, you're going to hit something and it's not really going to capture vortex. It's not going to create a vortex. You might have a trap vortex here, and that's going to be something similar to a wall or a step, which there is the traditional wall-bounded flow. So you will see a small recirculation zone. So I'm not going to change any of this. I'm going to keep this Spalart-Allmarus, curvature correction. I will change the inlet speed to make sure I have an appropriate y plus value. Since I'm not comparing to anyone, I could. I'm just going to make it 10 meters per second. I'm going to keep it purely in the x direction. Turbulent viscosity flow ratio would be 1. I've explained that in the past. Reference values, update that. Inlet. Coupled's fine. No pseudo transient. Can it hybrid initialize this? I have nice low of these values. That's a good sign. I don't really know, to be honest, what goes into that hybrid initialization. Um, but I do know that if it initializes and it starts off very high, that's not a good sign. So we can start the calculation and we'll see how this goes. Yep, it should. Alright, I'll watch it for the first, maybe 50 iterations. Make sure it's at least hopefully going down. And so at this 0 degrees angle of attack, I would imagine a higher drag compared to it without the slot, and I would actually possibly imagine a lower lift. So yeah, as in a zero lift, because there's now separation over the top. So that microscopic separation will actually cause, remember, as V goes down, P goes up. So there's more pressure on the top by just a little bit. So you would actually have some negative lift because the summation in the y direction of forces will then be in the y direction, or will be downwards. It'll be downwards. So I'll be back when this is converged, and we'll see what happens. Alright, so we're back. So I let it run for about 450 iterations. Something interesting is you see the residuals actually are crazy. It actually takes a while to even reach this point, and this is partly because of separation. As you can see in the velocity contour, there actually is separation over the top surface, but because of the external flow, it helps reattach this reattaches the flow to the surface. But in this calculation of separation, it just the way it numerically calculates it, you sometimes will have convergence issues. Whenever you're doing CFD of separation in general, you always run the risk of having convergence issues. And so it's pretty interesting what's exactly going on, and I could be totally wrong because you don't actually see a clear separation, like a recirculation zone. And so you kind of see it get as if it was a recirculation zone, but some of that eventually gets pushed over and rejoins this top surface. So it kind of is like this mixture of a recirculation zone, of a separation, that then gets reattached because of an external flow. And so you don't actually see this in a steady state problem. And so to backtrack, I guess there's many things why this doesn't work. Another thing is because it's steady state. And in reality, anything that to do with turbulence is a little bit iffy when you run it in steady state. So looking at the drag and lift, we have negative lift. As I said, negative lift corresponds to less velocity over the top. So at 0 degrees angle of attack, if the velocity on the top and bottom is the same, that means pressure is the same, that means lift is equal. But because we have less velocity because of separation, as V goes down, P goes up. So there's more pressure, some total Y pressure on the top and the bottom, meaning the net vector of Y force is down. Drag, because this is a vortex, because it's separation, you now have much more drag in the X direction. So comparing it to Spalart-Allmarus with, this is actually what I compared to, previously, and I matched it perfectly. You will now have much worse drag and lift. And in reality, this might not be how it is. But maybe what we could see is I'll try to run a 10 degrees angle of attack. So currently, the conclusion is this does not look good. This looks like we're seeing negative lift, more drag. And so what I'm going to do is I'm going to change the inlet to 10 degrees. Whoops. And I will apply this. Remember, for this, you have to create a negative when doing a lift. And so I am not going to reinitialize it, so I'm going to save this current solution, and then it's now just going to calculate it with a different value. And so we'll see how this looks. So my prediction, honestly, because I've never done this, I would not be surprised if this does not converge. And we'll see. We'll see. So we'll be right back. Hey guys, so I've let it run for over 1,000 iterations, and I want to show you that this doesn't really work out what you would expect it to be. So this bump actually onsets the separation, and it separates. This is standard separation, and it's average. It's actually kind of amazing that it even somewhat converged. It's not even fully converged, but it was. If you give it enough times, it might start converging. I actually stopped it because I didn't want it to start um, diverging. And so you actually will have, this is stereotypical behavior of where you're trying to find a steady state solution to something transient. So separation will create a wake and vortices that will, go after. And that behavior is transient. And so you're trying to take an average, which is what we're trying to do, take a steady state solution of something that's heavily transient. And so you get that type of behavior. In addition, you see the drag is huge, 0.058. We would expect a 10 degrees angle of attack to be 0.01. So that's a failure. And the lift is, yeah, that's not great. At 10 degrees angle of attack, they would expect it to be about 1, but it doesn't match up. So the point being that CFD is not able to capture in steady state any 2D vortex generator. So this is with an extrusion. One thing I can show you, so I think hopefully that proves it. I can show you actually something that I did previously that's a little bit interesting. It's actually with, instead of it being extruded, I had a dimple, a square dimple. One thing I can preface is some of you guys maybe want to do like that golf ball simulations where it is a curved dimple. Curved dimples are very hard to mesh in ANSYS Mesher. So I would highly recommend, you can take my word or you can put in the hours to realize it yourself, but it's pretty hard to mesh a curved part because it's, as I mentioned, you definitely likely cannot face mesh it. And I actually spent probably an hour trying to do one like that, and I ran into issues. So this is a similar one where instead I have a region here. And what I actually saw, it wasn't as bad as the other one. However, I saw this. This is the stereotypical recirculation zone. Flow would come in, get trapped, and it didn't it didn't show the energization of the boundary layer. Um, and this was at, I believe, 4 degrees angle of attack. Yeah, 4 degrees angle of attack. And I basically saw slightly less lift and slightly more drag. So once again, oh no, this is 10 degrees angle of attack. So actually, let's compare it. So 1.21, a little bit less lift, CD, 0.019, a little bit more drag. So this, once again, it converged, it looked better. Now, it didn't have a big separation, but there is a region of recirculation, which has adverse effects. If you guys are interested, you guys could maybe put a velocity inlet and have actually a synthetic jet. You can move this somewhere. So this is more discussion. In theory, if you want to study something, you can move this maybe towards the end. And actually, this is what a lot of people are trying to do experimentally. They're trying to prolong the boundary layer by re-energizing it, by actively putting in energy. That's where you enter plasma actuators. That's where that's the study of compressed jets, and you can add that near the end and see the effects. And so I'll let you guys do that study. And so hopefully this demonstrated and proved to you guys the difficulty of trying to simulate a vortex generator in two-dimensional and in steady state and using these turbulent models. So I'd highly recommend, if you're interested in doing vortex generator or boundary layer manipulation studies, it very likely has to be three-dimension. When you do it in three-dimension, you can take a planar contour that will produce something like this, but the solver has to take the vortex into consideration as a three-dimensional effect, um, and it probably has to be transient if you really wanted to get a good understanding. If you do a steady state, things are going to be averaged, and it might work out. To be honest, I don't know, but the computational resources will be much more. So hopefully this was helpful and really informative if you're interested in doing a CFD simulation of a vortex generator. Thank you.